Welcome to my video course on mastering ERTMS/ETCS signaling systems. If you're an engineer, a railway professional, or honestly just fascinated by the incredible tech that keeps our modern trains running safely at high speeds, you are definitely in the right place. Today, we're going to completely decode the massive, highly complex framework that governs the European Train Control System, or ETCS. We'll be breaking down exactly how the industry ensures that a train from one country can just seamlessly, and more importantly safely, operate on the tracks of another.
Here is our roadmap for this explainer. First, the Interoperability Challenge. Second, Technical Specifications, or TSI. Third, the System Requirements Specification, or SRS. Fourth, Understanding UNISIG subsets. And finally, Baselines and System Evolution. Let's kick things off with Part 1, the Interoperability Challenge.
To truly appreciate the engineering marvel that is ETCS, we first have to wrap our heads around the absolute nightmare it was designed to fix. Historically, Europe was operating with about 30 different completely incompatible legacy signaling systems. I mean, imagine a train traveling across borders. It practically had to swap out locomotives or carry this massive redundant stack of different antennas and computers just to read the local track signals. It made cross-border transport unbelievably costly and inefficient. There was a desperate need for a unified system, a universal language. And that system is ERTMS, with its core signaling component being ETCS.
So, how do you even begin to solve a monumental challenge like that? Well, you need a rock-solid governance structure. The political will actually kicked off back in 1993 when the EU Council issued the Interoperability Directive. Today, this massive undertaking is governed by the European Railway Agency, or ERA, which oversees all the modifications. But to actually engineer the solution, a consortium of major European signaling companies stepped up, known as UNISIG. Their job was to finalize the exact nitty-gritty technical specifications that make interoperability a reality.
Moving right along to Part 2, Technical Specifications, or TSI. This brings us to the very top of our document hierarchy. I mean, how do you mandate a unified system across an entire continent? You do it through the TSI, the Technical Specification for Interoperability. Think of the TSI as the foundational constitution of the European rail network. Set by the European Commission, it lays out the mandatory, high-level legal and technical goals. It essentially says that the old fragmented legacy systems absolutely must be replaced by the single, unified ETCS system. But while the TSI sets the target, it doesn't give you the granular engineering blueprint on how to actually build the train's computer. And that brings us to Part 3, System Requirements Specification, or the SRS. For that granular blueprint, we have to move down a level. If the TSI is our constitution, the SRS is the specific technical law enacted to enforce it. The key word here is behavior. The SRS is this dense, highly detailed rulebook that dictates precisely how onboard units, the computers inside the train, and the trackside equipment must interact. We're talking about defining every speed curve, every braking intervention, and every single display icon on the driver's screen. If you're an engineer building an ETCS component, the SRS is your absolute Bible. But, here is where things get kind of tricky. Early versions of the SRS were just written out in plain English text, what engineers refer to as prose. Now, human language is inherently ambiguous, right? When multiple software vendors, say a team in Germany and another in France, read a complex English paragraph describing a braking algorithm, they might interpret it just a little bit differently. And those tiny divergent interpretations meant that early ETCS equipment from different vendors still struggled to talk to each other perfectly. The human factor was literally creating a roadblock to true interoperability. So, to eliminate this human error, the industry has pushed hard to transition away from plain text. The goal of approaches like OpenETCS is to translate the informal prose of the SRS into strictly formal, mathematically verifiable, executable software models and APIs. By using formal methods and code generators, you leave absolutely zero room for misinterpretation. If the spec is a formal model, the software behaves exactly the same way, every single time, regardless of who manufactured the hardware. Let's dive into Part 4, Understanding UNISIG subsets. Now, the SRS is massive. We're talking thousands of pages of complex logic. To make this architecture even slightly manageable for engineers to implement, the UNISIG consortium cleverly sliced the platform into functional requirements called subsets. You'll hear these numbers thrown around a lot in rail engineering. Subset 026 is the big one. It acts as the core system requirement specification we just talked about. But underneath that, you have highly targeted rules. Subset 036, for instance, strictly governs the trackside Eurobalises, those yellow boxes between the rails that ping data to the train. And subset 037 dictates the wireless Euro-radio communications over the GSM-R network. Breaking it into subsets lets teams focus on standardizing one specific interface at a time. And when defining these interfaces within the subsets, UNISIG makes a super critical distinction between two types of specifications, FFFIS and FIS. Okay, so FFFIS, or Form Fit Functional Interface Specification, deals with strict physical and hardware constraints. It literally means a part must physically fit and connect in the exact same way. FIS, or Functional Interface Specification, on the other hand, deals entirely with the functional data protocols and software messages, totally regardless of the physical hardware shape. Knowing the difference between the two is absolutely vital for anyone designing ETCS components. Let's look at how this plays out in the real world. By strictly adhering to these subsets, we get flawless, secure data telegram transmission. For example, the subsets ensure that a trackside radio block center can format a data telegram, blast it through the air via the GSM-R network, and have the onboard European vital computer decode it perfectly. This is what allows the system to display a safe movement authority directly on the driver-machine interface, or DMI, right there in the cab. It's a perfect symphony of different subsystems communicating flawlessly simply because they all speak the exact same subset language. But this brings up a pretty massive operational question. With all these overlapping subsets and highly critical software requirements, ETCS is essentially a giant software network spanning a whole continent. So how on earth is it possible to introduce updates, fix bugs, or add new features without causing system-wide failures? Like, if one country updates its tracks, do all the older trains just suddenly stop working? Which perfectly tees up Part 5, Baselines and System Evolution. To avoid total continental gridlock, the industry relies on a very specific approach to version control called baselines. You can think of a baseline as a major, stable software amendment for the entire railway network. Rather than updating individual subsets randomly and hoping for the best, all the updated SRS subsets are grouped together, rigorously tested, and frozen into one stable release, like Baseline 2 or Baseline 3. This ensures that everyone across Europe is aligning their upgrades to the exact same version of the rulebook. And who manages this colossal update process? The European Railway Agency acts as the ultimate governing authority for these baselines. They take charge of the quality assurance, the configuration management, and the incredibly rigorous change request process. A vendor can't just casually change a line of code. It has to go through an extensive approval pipeline governed by the ERA to ensure safety is never, ever compromised. Of course, you can't just flip a switch and upgrade a whole continent overnight. Rolling out a new baseline requires a carefully engineered migration strategy developed jointly by the UNISIG signaling companies. The absolute #1 most critical element here is backward compatibility. They must guarantee that trains running older software can still safely operate on newly upgraded trackside infrastructure, and vice versa. It's a really delicate balancing act of optimizing software management while also managing the heavy financial realities for the railway operators. So, bringing it all together, we have what you could call the pyramid of interoperability. At the top, the TSI outlines the legal and technical vision. Below that, the SRS sets the exact behavioral rules. Then, the UNISIG subsets define the specific modular interfaces. And finally, the baselines control how the entire system safely evolves over time. By mastering this top-down hierarchy, engineers can guarantee an ETCS network where a train can cross multiple European borders seamlessly, entirely guided by a single, unified software language. Which leaves us with a truly fascinating challenge for the future. ETCS Level 2 is widely deployed, but ETCS Level 3 is right on the horizon, promising moving block technology, where trains actually calculate safe distances in real time without physical track sections. As our baselines evolve to support this immense complexity, how will our next generation of formal models and open-source specifications guarantee the absolutely zero-defect software required for full, high-speed automation? It's the next great frontier in railway engineering. As we push toward this fully automated frontier, we really have to ask, is absolute, zero-defect interoperability truly achievable across an entire continent? It's the ultimate challenge for the future of rail. Thanks, you can see in next video.